Here we're going to look at question 20 from section 2 of the ENGAA specimen paper. So in this question we're given the following circuit which has a thermistor in it with a resistance given by this function here. We're told some stuff about this function, that T stands for the temperature the thermistor's at, R0 is just R at T equals 0, mu is a positive constant, and we're told that B is greater than 1. So then we're also told a bit about this other component which is just labelled as X. We're told that X just has a very high resistance and emits light when the potential difference across it exceeds 2 volts. So with this information, the question asks us, for what values of T does X emit light? So what temperatures can the thermistor be at for X to light up? Now if you'd like to have a go at this question yourself, then please pause the video now. Otherwise, let's have a go. Okay, so to try and solve this question, let's have a bit more of a think about our circuit first of all. It's a bit of an odd circuit in that we've got a resistor or a thermistor which has a variable resistance, and we have this component X which seems a bit mysterious with a very high resistance. So we know that it lights up for this voltage Vx greater than 2V, but this is a component in parallel with this 200 ohm resistor, so it's going to have a voltage V1 across it, which is going to be exactly the same as this voltage Vx, the voltage across X. So when Vx is 2 volts or greater, then V1 is going to be equal to 2 volts or greater. But why is this going to be helpful? Well, we know that X has a really high resistance across it, and since it's in parallel with this 200 ohm resistor, then what we can say is that X has no current through it. Or at least it has no current through it for the sorts of voltages which we're looking at. So let's have a bit of a think why this high resistance means there's no current through. Well, the obvious thing is we can look at Ohm's law. So if we have a voltage across it, which is just a constant, and we have a really, really high resistance, then for this to be equal to V, I has to be really small. So for a really high resistance, then the current gets smaller, smaller, smaller. So here we're told that very high resistance means there's going to be absolutely no current through it. So since this is in parallel with our 200 ohm resistor, what we can do is we can just ignore X. We can ignore this component. Now another way of thinking about this, if you like, is that because it has a really high resistance, we can consider the total resistance of this portion. So if Rx is really big, then this 1 over Rx term is going to be really small. So you're basically doing this 1 over 200 plus something really, really small. So neglecting it doesn't really make much of a difference to the rest of the equation. So while it does technically have some resistance, it does have some current going through it, what the question is basically implying for us to do here is to ignore it and imagine that it has no current passing through it. So with that in mind, what we can basically do is just remove it from our diagram and try and think about the points at which our 200 ohm resistor has more than 2 volts across it, since this is just when X will light up as well. So the two things are going to be equivalent. Now that we've thought about the voltage across this component anyway, let's have a look and think about the voltage across the other component. So since we're looking for a minimum of 2 volts across this, we're looking for V2, the voltage across our thermistor, to be 10 volts or below. Now what we can do again is something which I think I've said before, is to try and always think about using Ohm's law. So let's go ahead and see if we can use Ohm's law on this component here. So we were told the resistance already of this component R, and we know the voltage across it has to be less than 10 volts. So substituting these values in, Ohm's law gives us this for our thermistor. So this equation we can see has a value of T in it. So how would we try and solve it for T? This is the temperature which we're looking for. It's a temperature at which this has less than 10 volts and therefore this has more than 2 volts across it. So the first thing to do is just to divide by the IR0 part out the front to give us this. Then of course we can take the natural log of both sides of this equation, which keeps our inequality sign being the same direction. While I've swapped the equations around the side here, it's still facing the inequality sign, is still in the same direction if you like. But then we divide by our minus u term, which is going to flip the inequality sign, since we're dividing by a negative, to give us this expression here. But rather than stopping just here, let's go ahead and use the negative to flip the sign of the natural log. giving us this final expression. So this is an expression for T, the temperature which we're looking for. But unfortunately, if we look at this equation, whilst we've been given R0 and mu, we don't know the value I, we don't know the current through the circuit. So the next step is to try and find this current, and then we will have our expression for T. Okay, so to try and think of some way of finding the current through our circuit, I, we need to come up with some way of doing that. So you might have guessed the thing which I'm going to say again, which is to always consider using Ohm's law. So what we could do is we could use Ohm's law on this 200 ohm resistor. Since we know the voltage across it is just 2 volts, and the resistance is going to be 200 ohms, giving us this. So we can divide by 200 to get the current is just 2 over 200, or 1 over 100 amps. Then, of course, we can just substitute this current into our equation for T, or expression for T. We find that T is greater than 1 over U ln of R0 over 1000. And then using the laws of logs, we can just separate our natural log into this, the log of R0 minus log of 1000. So this is just going to be our final answer, and you'll see corresponds to answer A given in the question.